Cerebrospinal fluid we just finished. That was one way to provide nutrients to the brain, carry away waste products, and in some cases, in some sense rather, protect the brain, cushioning the brain. Meninges are another way that we protect the brain. Meninges are layers that we've actually talked about since the first week of the semester. Now we're going to get into them in detail. Meninges line the entire dorsal cavity, including both the brain and the spinal cord. Dura mater is the outermost meninx, that's singular, with the epidural space and the subdural space below. So, next is the arachnoid mater with the subarachnoid space. We've been learning these in lab. We've been doing them for a while now. Subarachnoid space contains the arachnoid villi, which recycle the CSF. So remember, CSF flows through the subarachnoid space, and then the arachnoid villi, sometimes called arachnoid granules, will pump that into the dural sinuses, such as the superior sinus, superior sagittal sinus, which we see. Then finally, on the brain itself is the pia mater, the innermost meninx. And again, the mater, mother, dura, the tough mother, arachnoid mater, the spider mother, and pia, gentle, so the gentle mother. These are protective of the brain, all right, so that they're designed to keep foreign objects out, and if they get inflamed, we have meningitis, and meningitis can be extremely serious. Can be caused various ways. You can have viral meningitis, bacterial meningitis, or simply from chemicals like toxins. You can have, so meningitis just means you're inflamed. It doesn't say why. But almost always that's very serious. Meningitis is an extremely serious condition. So intracranial hematomas. Hematoma just means a big blob of blood, basically, all right? So don't know why this slide came up with all the text at once. My own incompetence. And it looks like it changes color as well. So the blues are different. Yeah, okay, fine. An intracranial hematoma is bleeding in the cranial cavity. Remember the body cavities, first week of the semester? You know, the dorsal body cavity consists of the cerebral, or the cranial rather, and the vertebral cavities. So it's possible to bleed into the cranial cavity. Now what do you think? Is that serious or not? Yeah, that's incredibly serious. Can be caused by trauma or by non-traumatic causes such as stroke. So let's look first at the subdural hematoma. Subdural is bleeding into the subdural space. It's the most common intracranial hematoma. And serious? Yeah. 60 to 80% mortality rate if acute. And so you can see in the diagram there we've got the blue. That's the subdural hematoma. So it's underneath the dura. Blood is continuing to collect in there. And what happens is when you get a hematoma, what it does is it increases the intracranial pressure. So you start building up pressure on the brain, and once you start squeezing the brain, now we're in big trouble, because now the brain can die from doing that. So we're talking about substantial brain damage potentially. Epidural hematoma is bleeding into the epidural space. That's typically, there's a lucid interval following a loss of consciousness. So people will hit their head, lose consciousness, and then they wake up and they seem like they're just fine. And then suddenly later they die. Mortality 15 to 20%. That's what killed both Gary Coleman and Natasha Richardson. And I don't know if you remember who those people are or ever even knew. Natasha Richardson was the wife of Liam Neeson. You know, Mr. Tough Guy fights the wolves and goes after his kidnapped daughter and everything. Lovely actress in many movies of her own and stuff. I think they were tobogganing or something like that. She hit her head, she was unconscious, woke up, thought she was fine, and died that night from the hematoma. And Gary Coleman was in a television show back in the, 70s, 80s. I never watched it, I remember. I don't remember. He was a guy who, what you talking about, Willis? Or something like that. I don't remember. I never watched it. Okay, but yeah, hematomas, or I think hematoma really is an old-fashioned word. I think they just talk about bleeding now into the intracranial spaces. Limbic system. We've mentioned this a number of times throughout these PowerPoints. And do you remember what I've said each time we've talked about it? Emotions and memory. So the limbic system is a group of disconnected brain structures. They're not all in one place. They're spread throughout the brain, but they're all somehow connecting and interrelating emotional things with memory. Not an anatomical structure, but a group of structures connected by function. Consists of the amygdala, the cingulate gyrus, the septal nuclei, the hippocampus, the dentate gyrus, the parahippocampal gyrus, the olfactory bulbs, the mammillary bodies, and the hypothalamus. And that'll be a question on the exam. It'll be a short answer. I'll say, name all the parts of the limbic system. No, I won't do that. I would never do that to you in a million years. But I'm reminding you because we've seen a lot of these structures before. All right? So, in combination, these structures provide links between memory, smell, emotion, and motivation. All right? And I don't know, a good example is that, you know how sometimes like you smell like cookies baking, and suddenly like out of nowhere you're back at grandma's house. You were 7 years old and you're playing with some toy, and you know your uncle's arguing with somebody, and you know you have all those things just come flooding back all at once. There's strong connections between those. We mentioned before, smell, memory, emotion. Very, very strong connections, and that's basically the limbic system. All these things linking together. You know, you smell some beans cooking, and suddenly you're back at Nana's house, and you know your uncle is lighting, your Dio is lighting farts or whatever, and yeah, you know these things just come flooding back. Hippocampus is where long-term memories are formed. It's not necessarily where they're stored, but where they're formed. So each day things happen to you, and you register them. And then remember we talked before about memory consolidation, one of the places of the mammillary bodies, again part of the limbic system. While you sleep, you kind of like file away all the day's events. And that's the hippocampus is involved in that. It's involved in storing your memories. It's where memory formation takes place. Damage to the hippocampus can cause you to lose your ability to make new memories. In which case, and this has happened, it was shown ridiculously in that movie 50 First Dates. There's an outstanding movie called Memento that's actually many neurologists and other scientists, neuroscientists said, wow, they actually got it right in the movies, like the only time. Watch that movie is Memento. It's awesome. About a guy who his wife was murdered and he sustained a traumatic brain injury that damaged his hippocampus. He was unable to form new memories, and he's trying to track down his wife's killer. It's a truly fabulous movie. It was actually named as one of the most 100 significant movies of all time or something. The Library of Congress has archived it, whatever. So hippocampus is where you form memories. That often happens during sleep. That's memory consolidation. Amygdala involved in fear and aggression, but communicates, again, in the limbic system. All these things are linked together. That's why an emotion can bring back a fear. Something like PTSD, certain kinds of stimuli. You encounter something and it brings back memories and it brings back the emotions, and the next thing you know, you're having a panic attack or you're suffering PTSD. So, limbic system, incredibly powerful and involved in so many human experiences. All those ways that emotions and memory and smells in particular are linked together. I know there's some kind of perfume that's been made since at least the 1970s, I guess, where I'll be walking through the grocery store or Target or whatever, and some woman will pass me and wearing that perfume. And within a matter of just seconds, without even being consciously aware, I'll find myself thinking that green-eyed bitch. Not talking about the women who just passed me, but the memory of a woman back from the 1970s who wore that perfume. Memories, emotions, smells, powerfully linked together. Interaction with prefrontal cortex provides connection with reasoning and emotion. Emotions can cloud your judgment, cloud your reasoning. This is what's going on. Sometimes that's beneficial, sometimes it's not. It's just the way the brain works. It could be, you know, I mean, having an emotional response to something, to fear, might help you realize, oh my God, I'm in a dangerous situation. See, so it could be beneficial, it could be adaptive. In other cases, maybe it's not. But that's the limbic system, okay, connecting all those things together. Reticular formation we've also spoken about several times along the way now. Not a distinct anatomical structure, but rather a collection of structures, all right? So a group of nuclei in the brainstem along with sensory fibers that project into the cerebral cortex, which are specifically known as the ascending reticular activation system, the ARAS. So this all goes together, reticular formation and the ARAS, all part of the same functioning structure. So it plays a major role in regulating consciousness, awareness, and attention. And important in regulating, for example, the transition between sleep and wakefulness. So maybe maybe you've had this experience. You know, you go to a party, maybe it was you had to work a double shift at work, and you're really tired, and you go to a party, and all of your friends are there, and there's music, and people are, you know, maybe drinking a little bit, and shouting, and saying silly things. It's a noisy, chaotic environment. You are super duper tired, and you sit down in a chair, and you realize that you're in a safe place. These are all your friends, everything's okay. So your reticular formation is kind of monitoring all of your senses and saying, you know, we're really tired and the environment here is safe. It's okay to sleep. And it basically flips that switch, and suddenly there you are in the midst of a loud, noisy, chaotic party, sleeping in a chair. And not from being drunk even, just from the fact that your reticular formation decided that we're tired, we need sleep, and it's okay to get it now. On the other hand, if suddenly there were gunshots, your reticular formation is monitoring your sensory input even while you're asleep. And if there are suddenly gunshots, your reticular formation will go, this might not be a good thing. And so it would wake you out of sleep. Okay? So see what I'm saying? So I can think of two examples. Let me see if I can give them relatively quickly. When I was after I got out of college, I was moved in with a friend of mine. We got an apartment together, 2-bedroom apartment. He had his apartment, he had his room, I had mine. We were living the crazy bachelor life. We were both working, you know, different hours, different schedules, and we were living the wild life. And so there was one night I remember, I had been out, I'd come home, I was really tired, I went to sleep. My roommate, Doug was his name, was out partying somewhere. And he came home, you know, like 3 a.m, just drunk. And decided for some reason, you know, like the way drunk people do, decided it would be good if we had hard-boiled eggs in the morning for breakfast. So he went over, he got a pan, filled it with water, put the eggs in, and then put it on top of our stove. We had an electric stove, you know, the kinds with the coils that glow bright orange. So he turned it on high, went over, laid down on the couch, and passed out. All right? So he's now completely passed out. The burner's glowing bright orange, water's heating up, water boils, all right, rolling, boil. The eggs are now cooking. The eggs get completely hard boiled. Burner's still bright orange. Doug's still passed out on the couch. Now the water starts evaporating out of the pan. Burner's still glowing bright orange. Doug's still passed out on the couch. Eventually all the water evaporates. The eggs are now sitting on the bottom of the metal pan right on top of the bright glowing orange burner. One by one they start heating up, turning black. Then they explode. Now there's exploded egg goo all inside the pan, and it's now being heated up, the bright orange burner on high. It starts creating smoke. The pan starts smoking. Pretty soon the whole kitchen fills with smoke. Pretty soon the whole house fills with smoke. And meanwhile, I'm in my own bedroom asleep, 3 o'clock in the morning. And I remember I woke up in the middle of the night. You know how sometimes you wake up in the middle of the night and you're not even fully awake. You just kind of like flip the pillow over to the cool side and then doze off again. So I remember I did that, and as I was dozing off, I thought to myself, wow, it's really smoky out today. And so it's like, boing, my eyes spring open. I'm going, wait, Tom, it's not supposed to get smoky in the morning. So I jump out of bed. I see, oh my God, there's smoke. My room's full of smoke. And I do like you're supposed to. I went over and I felt the door to see if it was hot, because there might be fire on the other side and you die if you open the door. It wasn't, so I went out. Room's full of smoke. I run out into the living room thinking I got to get out of the house, and there's Doug on the couch. And I think, oh my God, he's been overcome by smoke. So I prop the front door open. I start dragging Doug out by his feet. And of course, Doug at this point wakes up going, hey, man, what's happening? I drag him outside. I'm finally waking up and I realize, there's not all that much smoke. I wonder what's going on. So I work my way inside into the kitchen, and there I see this bright glowing orange burner with the smoke coming out of it. And I look inside, and there are these mushroom-like, completely charred remnants of eggs. Remember, I just opened the back door, got a hot pad, threw the pan out into the backyard. It's still there as far as I know. But in other words, it was my reticular formation that woke me up. When the room was smoky, the reticular formation said, Tom, it's not supposed to be like this. And it woke me up. And I never talked to Doug again. No, actually, we got along fine. But the damn apartment smelled like egg from that day on. We finally moved out. Actually, we got different places from that point on. Not because of that incident, just because we both ended up moving in with a girlfriend. So, okay, so that's reticular formation. Damage may play a role in narcolepsy and coma. So narcolepsy is where people fall asleep just, momentarily. It's a disorder. Coma. So in other words, that transition between sleep and wakefulness. Okay? Also involved in habituation, the brain's ability to ignore repetitive stimuli but still respond to meaningful stimuli. That's kind of what I was just talking about. How, like as a parent, you can sleep through a loud TV show, but man, the moment your baby cries, boom, you snap out of it. See what I'm saying? Those are both examples of the same kind of thing. Reticular formation, monitoring your outside environment even while you're asleep, and basically throwing that switch between sleep and wakefulness, knowing when it's safe to go to sleep and when, oh my gosh, we better wake up right now. Let's move on then and start talking about the cerebellum, which we said right from the start, one of the four main functional areas of the brain. We have the cerebrum, the seat of intelligence, thinking, reasoning, personality, memory, emotion. The brainstem, survival reflexes. The diencephalon, the command control center between the cerebrum and the brainstem. And now the cerebellum. Remember we said the cerebellum had a very specific role. Latin, by the way, means the little brain. It's the second largest part of the brain after the cerebrum. Major feature of the hindbrain in all vertebrates, the very back part of the brain. Comprises only 10% of the total volume, but accounts for over 50% of the neurons. So the cerebellum is neuron dense. It consists of these massive row after row after row of neurons. Tons and tons and tons of synapses. And remember what's its job? It's the part of the brain that smooths and controls movement in terms of making it fluid. All right, regulates things like balance and posture because there's so many muscles involved in just standing upright or walking. So remember, it doesn't send out the actual movement signals. That was the precentral gyrus, the motor cortex. And it wasn't involved in, the voluntary versus involuntary, like the basal ganglia, initiation, termination, all that. Its job is really just to sequence all those muscles. Like whenever you do any complicated movement, like, throwing a ball or like, flipping a pancake in a pan, those are sophisticated movements that require lots of muscles to be precisely coordinated and sequenced. That's what the cerebellum does. It's that coordination and control and sequencing and planning of the movement. Two hemispheres connected by the vermis, Latin, the worm. So there in that central illustration you see, it looks like a big worm in between the two hemispheres. That's the vermis. White matter forms the arbor vitae, the tree of life. So when you look at it from the side, you see all those white branches, all right? Tree of life, just a silly name for it, doesn't really have anything to do with anything meaningful. Transverse gyri called folia, Latin leaves. So notice you have the arbor vitae, the tree of life, and you have the leaves, and then you have the worm, the vermis. All we need is an apple, and we've got the Garden of Eden. Connects to the brainstem via the peduncles, Latin, that means the stalk. So remember, we have the pons and the cerebellum coming together. The pons was the bridge, so it's the cerebellar peduncles that are connected to the pons and the brainstem and allow communication between all of them. Cerebellum then, involved in the control of movement, coordinates signals from the motor cortex, the brainstem, and the sensory receptors. It's really where everything comes together. You know, it's monitoring where you currently are. It knows what it is you're planning to do, and its job is basically just to make all the muscles move at exactly the right time, at exactly the right amount of force, so that you make smooth, coordinated movements. Right? Determines the timing and pattern of complex movement. Has no conscious awareness, unlike the cerebrum. There's no thinking involved in the cerebellum, no conscious thinking anyway. Functions like an autopilot for movement, all right? It's so that you don't have to consciously think. You know, imagine you're going to reach out to get a glass of water. You don't have to consciously think, let's see, now I'm going to contract my biceps brachii and my brachialis and my coracobrachialis. Now I'm going to relax my triceps brachii. Now I'm going to stimulate my flexor carpi radialis. You can't waste time thinking about all that stuff. So the cerebellum is the autopilot. It's doing all that for you. Receives input from the vestibular nerve, cranial nerve number 8, to regulate balance and posture. So that's what it's doing. It's constantly monitoring. We'll see this when we get to the cranial nerves. Cranial nerve 8 is what is basically receiving and interpreting information about your equilibrium, about your balance, whether you're standing up straight, whether you're falling over, and so on. So the cerebellum is reading that information and then using the right muscles in order to make sure that you stay balanced, okay? Cerebellar fibers are ipsilateral rather than contralateral like the cerebrum. So therefore, whereas damage to the left cerebral hemisphere would cause damage on the right side of the body, damage to the left cerebellar hemisphere would cause a movement disorder on the left side. So it's ipsilateral, not contralateral. The premotor cortex of the cerebrum notifies the cerebellum of the intent to initiate movement. Remember, the premotor cortex was the staging or planning area for movement. It takes inputs from proprioceptors to allow the cerebellum to assess the current position. Again, the cerebellum wants to know, where are we now, what do we want to do next, and then it basically computes all the necessary movements to make that happen. Calculates a smooth, coordinated sequence of movements to achieve that goal. And the cerebellar peduncles convey the blueprint to the motor cortex. So notice information going in all different directions here. Cortex coming down to the cerebellum, cerebellum sending signals up to the cerebral cortex. All of this intended to make things work smoothly. Okay? And disorders of the cerebellum, as you can imagine, these would be disorders involving balance and movement and coordination of movement. So, again, cerebellar fibers do not decussate, so the dysfunction is ipsilateral. Damage to the left cerebellum means movement disorder on the left side of the body. No localization of function, as there were in the cerebrum. So deficits are global rather than local. So that's why cerebellar damage means damage to your entire body. You know, your arm, the movement, not damage necessarily, but inability to coordinate then movements of all that side of the body, the arms and the head and the neck and the leg and so on. Typical signs and symptoms of cerebellar dysfunction would include ataxia, impaired coordinations of movements, particular movements of gait, like walking. People with cerebellar damage have an uneven walk. They're kind of like, they're not walking straight lines. They're kind of like staggering, in different directions. Hypotonia, diminished resistance to passive movement. So like when somebody, tries to push your arm down, you naturally will kind of resist that. Hypotonia is a lack of resisting that. Postural changes, you don't stand up straight. Alteration of gait, again, you don't walk normally. Nystagmus, which is repetitive, uncontrolled eye movements, It's where your irises are jiggling around. You've probably seen that before in other people or in movies or whatever. Weak and irregular muscle contraction, again, because the cerebellum is trying to coordinate all that muscular activity. And dysdiadochokinesia, which is really cool. Inability to coordinate rapid alternating movements. So, like, imagine taking your hands and doing a tapping thing. Something like that. Inability to do that would be dysdiadochokinesia. Coordinating rapid alternating movements, can't do that anymore. Or like they show in that upper diagram, ability to roll your hands smoothly like that. Yeah, that's dysdiadochokinesia is when you have difficulty doing that. And then inhibition of reflexes. A lot of your reflexes are involved with the cerebellum, and so people will have a lack of reflexive activity if there's damage to the cerebellum.